Intimidating, fearsome, gruesome. Acid-base equilibria has claimed many victims, and we at Inkie Learning, we're going to stop that. We're going to guide you through how to tame this beast and turn it from a fiend to a friend. And you'll be joining and starting this journey with me, a small lizard, as we try to find a new friend. And let us begin this journey by looking ahead. There are 5 levels to conquering acid-base equilibria. And we're gonna do some preparation first by looking at the definitions of acids and bases. Alright, you should have learned this many months ago. But if you've forgotten or you're not confident in it, fret not. Let's do it again. Let's do our preparation proper. And the first definition you probably could give me is something that you've learned many years ago, that the acid is a substance that dissociates in water to produce the hydrogen ion or the hydronium ion, or a base that dissociates in water to produce OH minus. And this is actually called the Arrhenius theories of acids and bases. And you see 2 classic examples right there, hydrochloric acid and sodium hydroxide. So this is one of 3 definitions of acids and bases for the H2 chemistry syllabus. And of course, you know there are restrictions to the Arrhenius theories of acids and bases, where it's only applicable in the aqueous medium, right? How about the rest, where it's not necessarily in the aqueous medium? And that is where we have the 2 remaining definitions. The first major one, or the first of the remaining 2, is called the Bronsted-LOWLY acids and bases. Now, what does the Bronsted-LOWLY acid and bases really do? Well, it looks at the proton H+, whether it does the substance or the species donate the proton or accepts the proton. An acid would then be a proton donor. The Bronsted base would then be the proton acceptor. And a visual guide is shown right here. If you look at HA, it's going to donate the H to B, right? It's going to donate H plus to B, thereby forming A minus. And thereby you see this word conjugate base. Essentially, you can look at it as corresponding base, all right? And B would then accept the H plus and then gets the corresponding acid HB cation, all right? So we have 2 examples, the first being ammonia in water, all right? Ammonia, you notice, is going to accept a proton, thereby making it a Bronsted base. Water is going to donate a proton, making it a Bronsted acid. Now, ammonia's conjugate acid would then be this ammonium ion, so that is the conjugate acid for ammonia. Hydroxide ion is the conjugate base for our water, and we thereby have 2 pairs of conjugate acid base. Now, another example, the second one, hydrochloric acid in water. If you notice, hydrochloric acid is going to donate the H plus to form its conjugate base of chloride anion. That makes hydrochloric acid a Bronsted acid, and the chloride ion being its conjugate base. On the contrary, we have water accepting this proton, making it a Bronsted base, thereby having the hydronium ion being the conjugate acid of water. All right. And now what you notice is you cannot really remember or memorize, or actually you shouldn't memorize what species are Bronsted acids or what species are Bronsted bases, right? If you notice, for water, it could act as both or either a Bronsted acid or a Bronsted base. All right. So what you really look on is really just see who donates the proton, who accepts the proton, and then allocate correspondingly. So that's the second definition of acids and bases. Now we have the third, Lewis acids and bases, looking at electrons. So Lewis acids accept an electron pair, base donates an electron pair. Again, very simple representation. You notice the anion B has this lone pair that's going to quote-unquote attack the Lewis acid, forming the AB compound, forming a covalent bond. And because of that, Lewis base is assigned to be B minus, Lewis acid assigned to A plus. And we have a very classic example, boron trifluoride with ammonia. And you know that the lone pair is around the N atom, and it's going to attack the boron in boron trifluoride, forming the dative bond over here between B and N. Because NH3 is the electron pair donor, this would then be the Lewis base. Boron trifluoride is the electron pair acceptor, making it the Lewis acid. Now, if you notice, there's a difference between Lewis acids and bases with BRONSTED-LOWLY, right? BRONSTED acid is a proton donor, whereas over here, Lewis acid is an electron pair acceptor. All right, and it should kind of make sense to you, right? Because if really, you can make that association. Let's say for Lewis base, you can think of it as, okay, Arrhenius theory, I have OH minus, it has the electron, therefore it can donate electron, right? So you can kind of remember it through association, all right? Nonetheless, 3 definitions of acids and bases. The first one, Arrhenius theory, H plus OH minus, we're looking at aqueous, right? Dissolving in water or dissociating in water. Bronsted-Lowry, RO, so therefore we have pro-RO as well, proton or hydrogen as H plus. Lewis acid, second letter is E, therefore looking at electrons, all right? So 3 simple definitions of acids and bases. Hopefully that rang many bells. And let's move on to our second part of our preparation, looking at what we call by the acid-base conjugate pair. So over here we have ethanoic acid with ammonia, all right? And you notice that, hey, ethanoic acid is going to give us ethanoate, donating the H plus, making it a Bronsted acid. Ammonia accepts the hydrogen ion, making it a Bronsted base. All right, and that is where, well, we get the corresponding conjugate base of ethanoic acid is the ethanoate ion. Ammonium ion would be the conjugate acid of our Bronsted base, ammonia. And that is where we have the following. All right, the Bronsted acid is ethanoic acid. The Bronsted base is ammonia. The conjugate acid would then be ammonium. The conjugate base would then be ethanoic ion. All right, so this is an important identification and idea that we're going to bring on with us when we look at examining the reactions or the dissociations of weak acids and weak bases when we go to level 2. All right, so now we are done with level 1, or rather we are done with level 0. Time to start our journey and head towards level 1 in the next video. All right, catch you guys then, and let's get this done.